The periodic table of elements is probably the single most iconic image that has ever emerged in the entire history of science. But where did it actually come from? When I started making this video, I had no idea about the insane journey I was about to embark on. You see, within the last 150 years, there have been literally hundreds of unique attempts at creating a periodic table. This rabbit hole goes deep, and it is utterly fascinating. As the periodic table was pieced together over the years, so has our understanding of the very matter that makes up the universe. This video will be the first in a series of videos related to the periodic table, so make sure to subscribe so you don't miss the rest of the story. To help tell this story, I spoke to Professor Eric Sherry, who Academic Influence named as the second most influential chemist of the decade from 2010 to 2020. The main question I want to start with is it fair to say that you are the world's leading expert on the periodic table?
Well, I'm not the one to answer that question, but it has been said.
That's a very modest way of answering that question. If you want to learn about the periodic table, Eric is your guy. Okay, without further ado, let's go back to the beginning. The great thinkers of history have always been intrigued by matter. What are we and the rest of the universe made of? What are the simplest building blocks of matter? How many different types of building blocks are there? In the 5th century BC, the Greek philosopher Empedocles proposed that all matter is made up of 4 different types of building blocks, or elements.
The ancient Greek philosophers, the pre-Socratic philosophers, had a view that there were 4 elements: earth, fire, water, and air, and that all the things we see around us were essentially made of these 4 elements.
For more than 2,000 years, these elements were thought to be the fundamental components of everything you see around you. However, in the late 1700s, a groundbreaking discovery occurred that helped to usher in the birth of modern chemistry: the discovery of oxygen. Now, I've already made an entire video covering that story, which I'll link in the description below. But once oxygen was discovered, it was soon realized that air couldn't be a simple element like Empedocles had proposed, because it turns out it was actually a mixture of oxygen and other gases. Similarly, it was found that water was also not a simple element, but a chemical compound of oxygen and hydrogen. Shortly after this, the French chemist Antoine Lavoisier, often regarded as the founder of modern chemistry, proposed a new definition of what an element actually is.
In the case of chemistry, Lavoisier, regarded as the father of modern chemistry, took the step of defining elements as the last stage of purification or simplification. If you can't break something down any further, you have reached the stage of it being called an element. Now there's no talk of metaphysical elements, if you like. It's not an abstract view, it's a very concrete view of elements. Now, based on that, there was tremendous progress.
In 1789, Lavoisier published a book which included the first modern list of elements, with 33 simple substances. It was later decided that the top 2 on this list, lumière, meaning light, and calorique, meaning heat, were not elements, but this was a phenomenal leap in chemistry. By the early 1800s, the rate at which chemists were discovering new elements was increasing rapidly. With this new understanding of elements, it really was an exciting time to be a chemist. Another source of inspiration came from the English chemist John Dalton, who took a keen interest in identifying what elements themselves were actually made up of, and in doing so, he became the first scientist to develop atomic theory. The development of atomic theory ran in parallel with the development of the periodic table, and since I've already made a video about that journey, I'll put the link in the description if you want the full story. As more and more elements were discovered, chemists began to notice similarities between the chemical behaviors of certain elements. These similar elements had similar reactions and similar properties. They seemed to be related in some way. As a result, some chemists started looking into whether it was possible to classify the elements by grouping them together. However, with barely any knowledge of atomic structure, this was like trying to put a deck of cards into order when some of the cards are missing. You have no idea how many cards or suits there are supposed to be, you're not sure which cards go into which suits, and some of the numbers on the cards themselves might be wrong. As you can imagine, this proved to be extremely difficult. In 1829, a German chemist called Johann Wolfgang Döbereiner published a curious observation he'd made.
Dalton established atomic weights, and then when a consistent set of atomic weights had been achieved, and then that took some time. That took about 50 to 60 years after Dalton. Chemists and other scientists naturally looked at these atomic weights and tried to find relationships between the values. And a German chemist, Wolfgang Döbereiner, came across the idea of chemical triads. The classic example is lithium, sodium, and potassium. But there are many of these sets of three elements in which one of the elements has the average properties, meaning sodium has an atomic weight which is the average of the values of, if you add the value of lithium to the value of potassium and divide by 2, you get approximately the value for sodium. But even more significantly, the chemical reactions of sodium are somewhat intermediate between the chemical reactivity of lithium and potassium. You know, there's the famous experiment that we've all seen in school where you throw a little piece of each of these metals into a bowl of water. Lithium hardly reacts at all. Potassium reacts rather violently. It flips about on the surface, it catches fire. Sodium is somewhere in between. So with a triad, you have for the first time a numerical relationship which is connecting different elements. So this is a hint of some underlying structure, which turns out eventually to be the periodic table. But at that stage, people just recognized isolated sets of three elements called triads.
This was the first indication of some kind of numerical order to the elements. I want to take a quick moment here to give a shout out to the paid partners for this video, BetterHelp. Back in the 1800s, everything moved a lot more slowly, but today, in 2025, we live in such a fast-paced society that the pressure to avoid falling behind can sometimes feel overwhelming. Therapy is a great tool that can help to break down vague feelings of being left behind into specific, addressable concerns and concrete, actionable steps to improve your well-being. For me personally, I've spent 3 years working hard trying to juggle my YouTube channel as well as a full-time job, which has led to plenty of stress and frustration along the way. I'd never done therapy before, but I'd always been curious about it, and BetterHelp made it easy for me to give it a go. It's fully online, which makes it extremely comfortable and convenient. All you need to do is fill in a simple questionnaire, and in as little as just a couple of days, BetterHelp matches you with a suitable therapist from their diverse network of credentialed professionals. And if, for whatever reason, you don't feel that your therapist is the right fit for you, you can easily switch therapists at any time at no extra cost. I found it extremely refreshing to just have someone to vent my problems to, and I've received some great insights that have helped me already. Start fresh any day of the year with BetterHelp. Click the link in the description or go to betterhelp.com/chemistorian and get 10% off your first month of therapy. Okay, back to the video. Over the next few years, as more and more atomic weights were measured, another German chemist called Leopold Gmelin continued Döbereiner's work and found even more of these patterns. In 1843, he published a detailed chemistry book where he included a system that organized all the known triads and even some tetrads into a V-shaped table, starting with the non-metallic elements on the left and progressing towards the metallic elements on the right, with the elements generally organized by atomic weight. This was an amazing first step at organizing the elements, and sadly, Gmelin's work has mostly been forgotten from history. Currently, if you go onto the Wikipedia page for the history of the periodic table, there's no mention of Gmelin whatsoever. Another influential chemist who isn't mentioned here is the German chemist Max Joseph von Pettenkofer, who, in 1850, published an article which also looked at the numerical relationships between chemically similar elements. Specifically, he looked at the patterns between equivalent weights, which was a value that was determined by measuring how much of a given element reacted with a fixed amount of a standard acid. He found that the equivalent weights within certain groups of elements always seemed to increase by either the same number or by multiples of the same number, depending on the group. He even proposed that chemists could use these patterns to predict the equivalent weights for elements whose values would be difficult to measure experimentally. This novel idea of numerically predicting values would be very important later as the periodic table developed. The next big step took place shortly after Pettenkofer's publication by another German chemist called Peter Kremers. So far, chemists had only been looking for numerical similarities between elements that had similar properties to each other, which, to be fair, was a logical way to approach the situation. Kremers, however, took a broader look at the elements that had been discovered so far, to see if he could find any other patterns, and he discovered what he called conjugated triads. He found these two-dimensional groups of elements where there were both horizontal and vertical triad relationships between the equivalent weights. This was the first indication that there were numerical patterns that connected elements which weren't chemically similar, which suggested that perhaps the elements were all connected in some way. That unifying numerical connection was discovered not by a chemist, but by a French geologist called Alexandre-Émile Bégoyer de Chancourtois. Just like any good geologist, he liked to classify and systematize various minerals, and in the same way he tried to systematize the elements as well. In 1862, de Chancourtois devised a system whereby he arranged all of the known elements by atomic weight along a diagonal line. This table is 16 units wide, so that elements whose atomic weights differ by 16 will lie in the same column. By doing this, he became the first person to demonstrate something that today we call periodicity.
Now, periodicity is a further and more fundamental property whereby if you arrange the elements in order of increasing atomic weight as they did originally, as you move along that sequence, every so often you get an approximate repetition of a previous element. So you have lithium, you move through the atomic weights, you come to sodium, which is similar to lithium, you move again and you come to potassium, and so on. So this now begins to explain why triads were acting in the way they were, if you like. It's an explanation for triads, and it's the discovery of chemical periodicity. So chemical periodicity is more than just a one-dimensional sequence of elements. It's now a two-dimensional structure, two-dimensional system, which embodies the fact that elements repeat, approximately, of course, not exactly, after regular sequences.
De Chancourtois' periodic system was designed to be coiled into a cylinder, creating a periodic spiral. He called this spiral a vis-tellurique, or telluric screw, since tellurium is located in the middle. Sadly, de Chancourtois' very important work didn't make much of an impact on chemists globally, partly because the original publication didn't even include the diagram itself, since the publisher struggled to reproduce it. Another problem was that, although the telluric screw demonstrated many groupings successfully in some cases, there were other cases where chemically similar elements that should have been grouped together weren't. For instance, fluorine and chlorine weren't with bromine and iodine, despite it being well known that they all have very similar chemical behavior to each other. In my opinion, de Chancourtois' telluric screw is extremely cool, and it deserves a longer video dedicated to it, so make sure to subscribe because that video will be coming in the future. Around the same time that de Chancourtois published his system, there were many chemists who also threw their hats into the ring. The first was the English chemist John Newland, who, in the early 1860s, published several attempts at organizing the known elements into a table. In 1865, Newland developed his most famous system, which was based on what he called the law of octaves. Here's how it worked. On a piano, if you press a key and then go along by 8 keys, or 1 octave, you arrive at a different version of the same note. Newlands found that the exact same thing worked with elements when they're listed in order of increasing atomic weight. For instance, if you start at lithium, then move along 8 elements, you end up at sodium. Move another 8 elements along and you end up at potassium. We can think of all 3 of these elements as being different versions of the same note as each other, since they all have similar chemical properties. This was the first clear announcement of a new law of nature involving repeating properties of the elements after certain intervals in their sequence. However, there were problems with Newland's system. In order to ensure the law of octaves held true, he had to place some elements in the same space as each other in his periodic table. When Newlands presented his work at a London Chemical Society meeting, he faced fierce opposition from other chemists, who thought that his law of octaves was a bit too perfect to be true. One chemist called George Carey Foster said that Newland's method of organizing the elements by atomic weight and looking for patterns was completely arbitrary, and said that Newlands might have found similar patterns if he'd ordered the elements alphabetically. The chair of this meeting, William Odling, published his own system of classifying the elements around the same time. Similar to de Chancourtois, he also noted that when you arrange the elements by atomic weight, in several cases there seemed to be a repetition of the chemical properties between elements which were roughly 16 units apart from each other. Now, from a modern chemistry perspective, since the mass number is roughly double the atomic number, which is how we organize the periodic table today, this observation made by Odling and by de Chancourtois before him is essentially the same thing as Newland's law of octaves. In 1867, a German chemist called Gustavus Hinrich published a book describing his theory on the structure of matter. In it, he proposed a periodic spiral, with the elements increasing in atomic weight as you move out, and chemically similar elements grouped together on the same radial lines. But a system that really made progress was actually published 3 years earlier in 1864 by a German chemist called Lothar Meyer. Meyer's most unique contribution was that when ordering the elements, he intentionally left gaps in his table for elements that hadn't been discovered yet. For instance, he predicted that in the space below silicon, an element will be discovered with an atomic weight 44.55 units greater than that of silicon. At the time, chemists barely knew anything about atomic structure, so this was an extremely bold claim to make. Despite all of these publications, the concept of periodicity hadn't really caught on. Many chemists just weren't convinced that all of the elements could be united in this way. However, one chemist would eventually convince them all. The chemist who would go on to become the undisputed champion of the periodic table, Dmitri Mendeleev. Dmitri Mendeleev was born in 1834 in Siberia. His father, Ivan, was the headmaster of the local school, but he went blind the year of Dmitri's birth, and so Dmitri's mother, Maria, was left to look after Dmitri and his 13 older siblings all by herself. Because of this, she went to great lengths to support her youngest son's education. In 1849, when Dmitri was 15, she took him on a 1,500-mile journey by horse-drawn sleigh to try and get him enrolled in a prestigious school. He was rejected from the university in Moscow, but eventually was accepted into the teacher training school at the University of St. Petersburg, the same school his father had attended. Exhausted by the journey, Maria died a few months later. Dmitri was determined to make the most of the opportunity that had been given to him by her sacrifice. In the 1860s, he became a professor of chemistry at the University of St. Petersburg. By this point, as you can probably imagine from what we've seen so far, the world of chemistry was still very confusing. Atomic theory was still in its infancy, and new elements kept being discovered. Nobody knew how many would be found. All of these new discoveries were happening at a breakneck speed, and so when Mendeleev started teaching chemistry, there were no up-to-date Russian language chemistry textbooks, so Mendeleev began writing his own. He completed the first volume in 1868, where he covered the 8 most common elements, including hydrogen, oxygen, and nitrogen. However, this was only a tiny portion of the 63 elements that were known at the time. Mendeleev, who was struggling for money, knew that he had to pick up the pace with his second volume. On Friday the 14th of February 1869, Mendeleev sent the first 2 chapters of his second volume off to his publisher. To make a bit of extra money, he had arranged to do some consulting work the following Monday at a local cheese factory. In the meantime, he wanted to spend the weekend writing. His publisher was expecting the next chapter within the next 2 weeks, and he still hadn't settled on a way to organize the rest of his book. He quickly realized that rather than waffling on about each element individually, he would need to organize the elements into groups of elements that behave similarly to each other. He had already done this at the end of his first volume, where he described the halogens. Similarly, he had begun his second volume with a description of another family called the alkali metals. He decided to organize all of the rest of the elements into similar families, and he spent the weekend trying to figure out the best way to do it. Just like with previous attempts at organizing the elements, Mendeleev arranged the elements by atomic weight, and quickly noticed patterns. Like de Chancourtois and Odling, he discovered that, in several cases, there seemed to be a repetition of the chemical properties between elements which were roughly 16 units apart from each other. And, like Meyer, he intentionally left gaps so that elements lined up with elements that had similar chemical behavior. However, the more elements he included, the harder it became to fit some of them into his system. He spent the entire weekend obsessing over this, writing draft after draft, where he shuffled groups around and tried to piece everything together. On Monday morning, a coachman arrived to take him to the train station so that he could make his way to the cheese factory, but he told the coachman to wait. He felt that the solution was close, but just out of reach. He continued working for hours until he eventually dismissed the coachman altogether. The cheese factory would have to wait. That evening, he made a key realization. He had been sticking to the atomic weights far too religiously. When ordering the elements by atomic weight exclusively, you end up with a couple of elements that seem to be in the wrong place, like tellurium and iodine. But if you swap these 2 elements around, they both end up in groups that have similar elements to them. Iodine behaves a lot more like chlorine and bromine, and tellurium behaves a lot more like sulfur and selenium. With this small change, everything seemed to click into place. He continued working, and by Tuesday morning, he had completed his periodic table and quickly got it published. Now, unbeknownst to Mendeleev, he wasn't the first person to make this swap. Newland, Odling, and Meyer had also swapped iodine and tellurium in their own periodic tables for the same reason. But what really set Mendeleev apart was the fact that once he realized this and pieced everything together, he became so confident in his system that he used it to claim that some commonly accepted scientific facts were wrong. Let's look at an example of this by looking at Mendeleev's placement of beryllium. In 1871, Mendeleev published another periodic table which had some tweaks compared to his 1869 table. At the time, beryllium was commonly assigned an atomic weight of 14, which was the same as nitrogen. However, Mendeleev thought that this simply had to be wrong. He argued that this would place beryllium amongst the non-metals on the right-hand side of his table, which wouldn't make any sense because beryllium is clearly a metal. And not just any metal, but beryllium's chemical properties were very similar to the other metals in group 2 of his table. Because of this, Mendeleev proposed that the actual atomic weight of beryllium must be around 9, placing it in group 2, right above magnesium. In the 1880s, more accurate measurements of beryllium's atomic weight were taken, and it was found to be, you guessed it, 9. Mendeleev was right all along. Now, this was already amazing stuff, but he even took it one step further. Not only did he predict that some elements' atomic weights had been measured incorrectly, he also made detailed predictions about elements that hadn't even been discovered yet, by looking at the elements around their gap in the periodic table and averaging out their properties.
A great example is the undiscovered element that he left a gap for in his table underneath aluminium,
which he preemptively gave the name Ika aluminium, using the Sanskrit word for 1. Mendeleev predicted that an element would one day be discovered with an atomic weight of around 68, which would fit here, and he gave a detailed list of what its chemical and physical properties would be. In 1875, a French chemist called Paul-Émile Lecoq de Boisbaudin was investigating a 52-kilogram sample of a mineral called sphalerite, taken from a mine in the Pyrenees Mountains. While experimenting on this huge chunk of rock, he was able to obtain a few milligrams of a substance which, when analyzed spectroscopically, seemed to show the lines for a new element. Later that year, he obtained several hundred kilograms of the same ore, from which he was able to isolate around a gram of this previously unknown metallic element. He gave the element the name gallium, from Gaul, the ancient name for his home country of France. De Boisbaudin found gallium to have an atomic weight of 69.96, very close to Mendeleev's prediction. However, there was a problem. De Boisbaudin measured its specific gravity, which is essentially its density relative to water, as 4.7, but Mendeleev had predicted that its specific gravity should be around 6.
The Frenchman reported the specific gravity of his new element, but it conflicted with what Mendeleev had predicted. So Mendeleev had the audacity to say to him in writing, no, I think you may be wrong. Why don't you look again, measure it again, and I think you'll find it to be more like such and such a value. And sure enough, the Frenchman repeated the experiment, and Mendeleev had been right. So this is almost like magic. You know, Mendeleev, miles and miles away in St. Petersburg, knew the properties of this element better, in a sense, than the man who had it in his hands and should have known the properties, if you like.
Predictions like these led to the widespread acceptance of Mendeleev's periodic table. As new elements were found, they filled many of the gaps Mendeleev had left. For a while, Mendeleev's periodic table worked pretty much perfectly, but the first real challenge came in 1894, when the Scottish chemist William Ramsay and the English physicist Lord Rayleigh discovered an element that didn't seem to fit anywhere in the periodic table: argon. It was unlike anything that had ever been seen before, and its properties were completely unique. Unlike other elements whose reactions chemists were able to investigate, argon had no reactions. It didn't react with anything whatsoever. Also, rather than forming molecules like all other known gases, argon floated around as individual atoms. Mendeleev was convinced that Ramsay and Rayleigh were wrong. This couldn't be a new element, it just didn't fit anywhere. In an article published in Nature in 1895, Mendeleev said, "If we suppose further that the molecule of argon contains 3 atoms, its atomic weight would be around 14, and in such case, we might consider argon as condensed nitrogen, N3. That same year, Ramsay discovered another element that had previously only been observed in the sun, helium, and after investigating it, he found that it had a lot in common with argon. Now, there were 2 strange elements that didn't seem to fit anywhere. Mendeleev's periodic system seemed to be failing to accommodate these discoveries. 3 years later, in 1898, Ramsay discovered 3 more elements: neon, krypton, and xenon. By this point, there was no doubt that these were indeed brand new elements, and they all needed places in the periodic table. The story of the discovery of the noble gases is one of my absolute favorites, and if you want to know how they did it, I've already made a video all about it, so I'll link that below if you want to check it out. In the spring of 1900, Ramsay met with Mendeleev in Berlin and suggested to him that his noble gases could be placed in an entirely new group on the right-hand edge of the periodic table, thus extending each period by 1. Mendeleev agreed and later wrote, "This was extremely important for him as an affirmation of the position of the newly discovered elements, and for me as a glorious confirmation of the general applicability of the periodic law." 2 years after their Berlin meeting, Ramsay published the 2nd edition of his book, Gases of the Atmosphere, which I have an original copy of. In it, he includes this new form of the periodic table, now featuring an 8th column for his noble gases. There's also this interesting slip, which, when folded over, changes the elements in each group. Ramsay said that this slip was included to show that the elements represented on it have a double set of resemblances. I showed this to Eric during our interview, and he'd actually never seen anything like it before and was keen to do some research into it.
Thank you for pointing this out. This, I think, deserves a lot more attention and maybe an article or 2.
Yeah, for sure. We can talk about it later after this. I will send you pictures of it.
You've reminded me of the importance of archival research, and maybe it's something we should have done more of.
I'm glad to hear it. With the general acceptance of the periodic table, there was a growing sense that the work of chemistry was pretty much complete. Thanks to Mendeleev, chemists knew that they had discovered the majority of the elements, and that all that was left to do was to find the remaining elements to fill in the last few gaps in the periodic table. With that, we would know all there is to know about the fundamental, unchanging building blocks of matter. But at the start of the 20th century, a startling discovery was made that completely upended chemistry in a way that nobody was expecting. Suddenly, the impossible seemed possible. It seemed that some of these immutable, unchanging elements could change into others. The person who made the discovery would go on to become one of the most famous scientists of all time,
Maria Skłodowska-Curie.
and she deserves an entire video to tell her story. Make sure you subscribe so you don't miss it. Before you go, I want to ask for your help. This video series was an enormous project which I made by myself in my free time, but I want to be able to divert more time and energy to videos like this, and your support can make that happen. If you'd consider liking, subscribing, commenting, sharing, etc., that would tell the YouTube algorithm that this video is worth watching, and it would really help me out. My goal is to get to 100,000 Chemistorians by the end of 2025, so if you made it this far and you want to help out the channel, I'd really appreciate your support. Thanks again to Professor Eric Sherry for all his help in making this video. He literally wrote the book on the periodic table, which I read in preparation for this video. It is fantastic, and it goes into way more detail than I ever could in a single video. So if you want to learn more, I strongly recommend checking it out. Head over to ericsherry.com to find more of Eric's work. Also, I plan to post the full unedited interview with Eric in the coming weeks. It was fascinating talking to him, and during our conversation, we might have accidentally stumbled on a historical discovery together. So this Ramsay one might be some kind of intermediary between the 8 and the 18. That's fascinating.
Yes, because he doesn't seem to have realized that you can avoid that slip of paper in a way by moving to an 18-column table.
That's so cool.
So it would be nice to contrast this with the eventual 18-column table.
Wow.
And then look into whether Ramsay had any correspondence with Werner, and so on.
That's amazing. I can't wait to find out more about this. That's so interesting. Make sure to subscribe so you don't miss it. Thanks for watching, and I'll see you in the next one.